In subtopic 11.2, we briefly looked at capacitors as a way to smooth the output of an AC rectifier. So in subtopic 11.3, we're going to look at what capacitors actually are. So a capacitor is an electronics device that basically just consists of two plates. So fairly simply, a capacitor consists of two metal plates that are separated, and separated by an insulator. And to be very specific here, it's an electrical insulator. So for an electrical insulator, it's not going to conduct current. So there's no flow of electrons from one plate to the other. We're only going to see electrons moving around the rest of the circuit and not through the insulator. When we're talking an insulator, we could be looking at things like air, but usually you'll have, say, a plastic or a ceramic that's between the two plates. So in terms of a diagram, at its very simplest form, you can think of a capacitor as containing the two plates. It looks something like that, and in between the two plates we would have our insulator. So that insulator keeps the two plates separated, and as we'll see later, it also can affect the way that the capacitor operates as well. So that's sort of the basic structure. So we've got these two plates either side, so one there, and the insulator in the middle. Now those two wires that I've drawn off each side are the connecting wires that you would connect to the rest of the circuit. The circuit symbol for a capacitor, it's basically just sort of a representation of what the capacitor is. So two even lines that are parallel. Looks kind of similar to the symbol for a cell, except that the lines here are equal in size, whereas for a cell one's longer than the other. And it's sort of helpful to keep in mind that there is a similar aspect about cells and capacitors, in that the function of a capacitor is to separate charge. So with a cell, we start off with charges that are separated, and so we allow a current to flow. But for a capacitor, the function of a capacitor is basically to separate charge. And in the same way that a cell, when it starts off with charge being separated, that then means that we're also going to store energy as well. So when you've got charges separated, work has been done to separate the charges, and so a capacitor will actually store energy in the process of storing charge. Now, when a capacitor is connected to an EMF, that's where we're going to get this charge separation happening, and we'll have a look at that, how that actually occurs, and the process, I suppose. So there's going to be a build-up of charge over time as we allow electrons to move. So the electrons are going to be removed from one plate, and if we remove electrons, then that means that plate is going to become positive. And as the electrons are then removed from that plate, they're then deposited onto the other plate, and if we've got then a build-up of charge, that will mean the plate becomes negative. So in that process, we've got that, as I said, we've got to do work on those electrons in order to separate them in that way. So if we look at that in a diagrammatic sense, so if we've got a very simple circuit here showing a capacitor connected to a battery made up of multiple cells, what the battery is effectively doing is, if we imagine, say, a single electron that was positioned here, and we're going to take that electron and drag it away from that plate, and in dragging it away we're going to leave an extra or a positive charge behind. So this electron then is now going to be moved around the circuit, and it's easiest to think of it as the electron moving the whole way around the circuit as it is forced by the EMF. Really it's sort of a chain reaction, and electrons are pushing one after the other, but ultimately this electron then travels all the way around the circuit and then is deposited on the other side. Likewise, if we continue that process, we'd then have another electron that would be going through that whole loop around the circuit and end up on the other side, and then we could have a whole build-up of charge on each of those two plates due to the electrons being moved around the circuit and causing one plate to become positive and one negative. And you'll notice that the positive plate is connected to the positive terminal of the battery, and the negative plate is connected to the negative terminal of the battery. Now initially, when the plates are neutral, a large current will flow. So when we first connected up the circuit, a very large current is going to flow, and that's because there's nothing really, no excess charge anywhere, and so we can have a lot of electrons flowing through the circuit. Now when we talk about the large current flowing, what we're really saying is that we get these electrons moving around the circuit in this orientation, from the positive plate through to the negative plate. It effectively then looks as though there is a current that flows the whole way around the circuit, including across the capacitor. As we said before though, no electrons actually move across that gap, they only travel around the rest of the circuit. So initially a large current flows, and as more electrons are deposited on the negative plate, we end up with less and less current flowing. And the reason for that is that we get a large build-up of charge, and the large build-up of electrons on the plate already make it harder to put any more electrons on. So less and less current flows, and the reason for that is due to the electrostatic repulsion. Sorry, let me just fix that. So that's due to the electrostatic repulsion between the electrons that are already on the plate and the electrons that are sort of flowing through the circuit. And so eventually the current will decrease to zero. Mathematically speaking, the graph that we would see for the decrease in the current is actually an exponential decay. So as a result, so just quickly, if we were to look at the current over time, then we'd see that initially it starts quite large and decreases and would be asymptotic on the horizontal axis, so never actually getting to zero. But for all practical purposes, if you're using an ammeter in the circuit, you would notice that the current does eventually decrease to zero. Taking this another direction now as well, if you cast your mind back to subtopic 5.1, we looked at if we separate charges and the electric field that's produced between them. And here, if we separate the charges, we're also going to get that electric field set up between the plates, and along with that, that's actually going to result in a potential difference. So across the plates, there is a potential difference that is built up between the plates, and the more charge that you separate, the larger the potential difference becomes. And the size of that potential difference can get no larger than the EMF that's causing the separation of charge to begin with. So if we look back up at that graph, sorry, eventually equal to the EMF. So if we go back up to this graph, if we were looking at, say, EMF or potential difference in orange instead, that would start off at 0 because initially there's no separation of charge across the plates, and would then increase and flatten out, where the asymptote in this case would be the EMF of the cell. So you can see there that as current decreases, the the potential difference across the plates increases. Note that the two scales there for the purple and the orange don't actually interact, or they're not the same. So that the fact that that orange line is close to the top of the current, that's just coincidental in this situation. So if we're now looking at how much charge a capacitor can store, that would be the property that we're referring to is the capacitance. So capacitance, it's represented by the symbol C, is the storage capacity, I suppose, is the way to think of it, of a capacitor. And it's calculated as the found by the ratio between the charge that can be stored and the potential difference between the plates. When we're talking here about the charge that can be stored, we're only really talking about the charge on one plate. Because if you think about it, if you were to add up the charge on both plates, you'd have a total of 0, given that the charges would be equal but opposite. So when we're dealing with charge here, think about it as just being what the amount of charge that has been pulled off the positive plate and deposited onto the negative plate. And in this case, we're not worried about the fact that it's negative. We're just dealing with the amount of charge, so we can ignore the negative value there. So the capacitance, as I said, ratio between the charge that can be stored and the potential difference between the plates. And the equation then should be fairly obvious from that definition, is simply just C is equal to Q on V. So that equation there is an important one. That's in the data booklet, so I'll highlight that one. And the last little note here is that capacitance is measured in farads. So as with a number of quantities and various things in physics, it's named after a scientist, being Michael Faraday. The symbol there is F, and you can see that the units for F are equivalent to, so if you look at the units for charge as coulombs, and the units for potential difference is volts, so 1 farad is 1 coulomb per volt. So just as a little side note. Now, one last little note here too is that 1 farad's an extremely large capacitance, so you won't usually come across capacitors that are that large. You might in, say, large energy storage facilities where you need large batteries that can store lots of charge, so you might have capacitors there that are extremely large. But generally speaking, any electronics device that you might come across, or anything that you might open up and have a look at, the capacitances would generally be no bigger than millifarads, and more commonly in the microfarad range. So that's due to the fact that if you were to store 1 coulomb of charge per volt, that's a very large amount of charge, and it doesn't usually happen.